Okay, so in this lecture, we're going to get through all the theory, okay, in a nutshell. All the theory that you need in a nutshell about electrodynamics to start getting into all the applications. Okay, so just like I did about quantum mechanics, I'm going to do a 20-30 minute nutshell for electrodynamics. Okay, so all the theory of electrodynamics is summarized in the 4 Maxwell's equations. Okay, so we're going to study about electrodynamics. And all its theory is summarized by the 4 Maxwell's equations. Now we'll learn one by one what each equation is and how we obtain them. Okay, so the first equation that we learn is, it's got a name, it's called the Gauss's law. Okay, so Gauss's law in, so it's called the Gauss's law in electrostatics. And these are pretty elementary things that you would have studied in your 11th and 12th. Okay, so we would have studied about the Coulomb's law, which gives the force between two charges, right? So 4 pi epsilon naught q1 by q2 r square, q1 q2 r square, right? So this gives you, this is the Coulomb's law that gives you the force between the two charges. And we define an electric field, right? So E is the electric field. It gives you the force a unit charge will experience because of a source charge Qs, right? So F and Q, E are related by this equation, right? So electric field is the force a unit charge will experience because of a source charge. Okay, so it tells you how much, what the strength of the field is. Okay, so what the strength of the field is. So if the unit charge is attracted by a stronger force, it means that the strength is more. Okay, so Gauss law, what Gauss law says is, you take a charge. Okay, so you take a charge, you take some charge, source charge Qs, and close it by a closed Gaussian surface. So we pick a sphere, a spherical surface, for mathematical simplicity, okay, which we will derive. Now, we from Qs there is the flux coming out, right? So you would have studied about flux in your lower classes. So what flux just means is the number of electric field lines coming out. Okay, so the number of electric field lines that come out. Okay, it represents. So if the lines are denser, it means the electric field is more strong. Okay, so this flux that I will define this way mathematically, flux, this phi is the flux. It is nothing but E dot dA. Okay, integral E dot dA. So this captures all the field that is coming out. Okay, now if you perform this integral E dot dA, what you get is Q by epsilon naught. Okay, so Qs. Okay, right, we got the source charge we named as Qs, right? So Qs by epsilon naught. So I'll remove this S, okay, so that we don't get confusion later on. So this, if you perform this integral E dot dA, you get an answer Q by epsilon naught. So this is always true. Okay, so this is always true in the case of electrostatic, and this is called the Gauss law. Okay, this is the Gauss law, and this is in integral form. Okay, this is the Gauss law in integral form. You can of course get the Gauss law in differential form. Now, how do we get it in differential form? Use the divergence theorem, Gauss divergence theorem, right? So E dot dA can might as well be written as the divergence of E, the volume integral, integrated, the volume integral is equal to the charge density. Okay, the charge density. And when you integrate, so the total charge can be represented by the integral charge density integrated with respect to the volume. So we do the volume integral over the volume charge density, you get the total charge. Okay, so that's nothing new. So now this can, now if you just remove the integral, the volume integral on both sides, you will get the differential form, the Gauss law in differential form. So this is your first Maxwell equation. Okay, so Maxwell didn't find out all the 4 equations. So he fixed the last equation that we will talk about, and after that we call all of them the group we call as Maxwell's equations. So this is Gauss law in differential form. Gauss law in differential form. Now let us go to the second Maxwell equation. Okay, so the second Maxwell equation is going to be Gauss law in magnetostatics. Okay, so this is going to be Gauss law in magnetostatics. So we're going to take, so this was electrostatics. Let me write it. So this is going to be magnetostatics. Here we consider static charge. Here we're going to consider, let's say we're going to consider a magnet that is stationary. Now if you consider a magnet that is stationary, okay, let's say north and south pole, right? North and south pole. Now how does the magnetic field lines of the magnet look like? So it starts from the north pole, ends in the south pole. Starts from the north pole, ends in the south pole. So if I took, let's say if I took a spherical sphere, okay, if I take a sphere like this, now what is going to happen from here? It is the field is going to come out, so it will get a positive contribution. The flux will get a positive contribution, right? The flux is going to get a positive contribution, and here the field is going to go in, so it will get a negative contribution. And similarly everywhere, so it's going to come out here positive, going to go in here negative. So therefore the total flux will be zero. Okay, so the total flux will be zero in magnetostatics. So flux, we said mathematically we can call it B dot, there it was E dot dA, so here it is E dot B dot dA. So there it was E dot dA, here it is B dot dA, magnetic flux. So this is equal to zero. So this is your second Maxwell's equation. So this is the second Maxwell equation, different integral form, and in differential form you can just convert it in differential form, just apply the Gauss divergence theorem. It will become B del dot B is equal to 0. So this is the differential form. This is the differential form. So remember, all this was this is happening in empty space, right? Because we are using epsilon naught, right? We are using epsilon naught. This is the permittivity of free space. And there in magnetic field, when we come to use magnetic field, nu naught, which is the permeability of free space. We will come to use that. So that will become significant later. Okay, so I'll tell you why I'm telling you that, right? Okay. So the next Maxwell equation. Okay, so the next Maxwell equation comes from the Faraday's law of electromagnetic induction. So what does Faraday's law say? EMF induced is equal to minus d phi by dt. So the rate of change of flux is equal to the EMF induced. So this is the statement you would remember from your lower 11th and 12th classes, that this is your Maxwell's Faraday's law of electromagnetic induction, right? So this, I'll write it out. So this is your, so third Maxwell's equation comes from Faraday's law of electromagnetic induction. Right. This is your. So now this EMF, what is this EMF? So this EMF, you remember the definition of the EMF is nothing but the force required. So it is actually a work done. So it is a very misleading term to say it is an electromotive force, because it is actually a work done, because it is the force required to carry the unit charge across the entire circuit, right? So it is nothing but E dot dl, closed loop integral E dot dl, because it is the E is the force of a required by a unit charge, of a force on a unit charge, and integral, closed loop integral dl means across the entire circuit, right? So this is the work done. This is the work done in moving a unit charge across the entire circuit. So E dot dl is equal to minus d phi by dt. So this, so I hope you understand why I'm writing it this way. Now again, d phi. Okay, so phi is nothing but integral b dot dA, right? So phi I can write as, so phi I'm writing as b dot dA. So integral b dot dA. Okay, so again we can use the Stokes theorem. I'm going to use the Stokes theorem. So this is, so this I can write as, so this is essentially the Maxwell equation, third Maxwell equation in differential integral form. Okay, so this is the integral form. Now if you use the Stokes theorem, what you can do is you can convert, this is using the Stokes theorem. So this will become del, the curl of E. Okay, so the curl of E dA is equal to, so here it's the same thing. So minus dA. So I can remove the surface integral on both sides, the area integral, and this will just become del cross T equal to. So all these theorems, Gauss divergence theorem, Stokes theorem, all these come from vector calculus. Okay, so in physics, your mathematical physics and all the other topics will go together. All of theoretical physics will be written in mathematical language. So therefore, you will need your mathematical physics background completely. Okay, so this is your differential form. Okay. So we've completed three Maxwell's equations. So let's go to the fourth Maxwell's equation. Okay. So this actually is called the Ampere's circuital law. This also you might have studied. So even if you didn't, I'll just tell you what it is right away right now. So what it tells is, if you have a bunch of currents, okay, so if you have a bunch of currents going like this, let's say they're going like this. Okay, so this is, okay, and they cut through a closed path. Okay, they cut through a closed path. Okay, so this is a circular loop. So this is current I1, this is current I2. They are both cutting through the circular path. Okay, and if you calculated B dot dl, B dot dl. Now this B dot dl is calculated along this path. Okay, so as I'm pointing out, you can see it is calculated along the path of this loop that we've taken. Okay, this closed loop that you've taken, it is calculated, B dot dl is calculated along this closed loop path. So you must understand what this means. Okay, so I've done in line integral. Okay, so I've done what the line integral means in my mathematical physics videos. You might watch that, but I might just tell you here. Okay, so if you actually divide this, okay, so B was the magnetic field, and let's say you're dividing it into so many parts. Okay, so let's say this is part 1, I'm calling it dl1. Let's say this is part 2, dl2. Okay, likewise dl3, part 2 is dl3. Now B dot dl calculates B1, which is the field in the region dl1. So, and B1 dl1, and the field in the region dl2 is B2 dl2, and goes on like that. Okay, for each segment goes on like that. So each segment goes on like that, and you find the summation. So Bi dli. So when you change it to the continuous, when you do the continuous integration from the discrete to the continuous integration, we get b dot dl, integral b dot dl, and this integral always turns out to be mu naught I. So I is the current enclosed. So in this case, the current enclosed is I1 and I2. Okay, so in this case, the current enclosed is equal to I1 and I2. So if you have, let's say, if you have a current in the opposite direction, like current cutting through the loop, okay, so it cuts through the loop in the opposite direction. So it has to pass through the loop. Okay, so that's why I'm drawing it like this. So it's passing through the loop. So then you will, since it's coming in the opposite direction, you will have a negative sign. Okay, so you will have a negative sign. So this is what it means. So this Ampere's circuital law is given here. So let me rewrite it here. So this forms the fourth Maxwell equation, mu naught I. So again, you can convert it into the differential form by using the Stokes theorem that I just used. So using the Stokes theorem, this will be del cross B dot PA mu naught and this current can be written as, you will remember the term J, right? So J is the current density. So the total current can be obtained as J dot dA, integral J dot dA. Okay, so J is your current density. So you might recall that J is your current density. Just so we had rho for charge density, J is your current density. Okay. So this just becomes, if you remove the integrals on both sides, the area integral just becomes J. Okay. So this is your fourth Maxwell's equation. This is the differential form. This is your integral form. This is your integral form. So this is, so remember this J is your current density. Okay, so let me write it out now. Let me just write it out, all the four together. Maxwell's equations. So first is your Gauss theorem. So these are your four Maxwell's equations in differential form. Now, what happens is, this is your four Maxwell's equation. Now, I was telling you about the fix of Maxwell, after which this came to be called the four Maxwell's equation. Now, it turns out that this fourth equation, there is a problem with this fourth equation. Okay, if you do, the divergence of a curl is always zero. Mathematically speaking, the divergence of a curl is always zero. So this should be del dot. So let me take the new outside. So del dot J, right? So del dot J. Okay. So now the left hand side is zero always by identity. Okay. But the right hand side is zero only when the charge is flowing uniformly. Okay. So supposing there is a conductor here, and if the charges that are here are flowing uniformly, okay, uniformly they are flowing, then the divergence will be zero. Okay. So when you, again, there is a lot of the mathematics here is important to understand. So that's why I said in my videos in vector calculus, you'll see about divergence. So see what it means. So if the flow is uniform, the divergence is zero. Okay. If the flow is uniform, the divergence is 0. So here it's the current density. So if the current is flowing uniformly, then the divergence is 0. But for non-steady currents, okay, for non-steady currents, the divergence is not 0. Currents del of J is not equal to 0, and therefore this equation will turn out to be, will become a problem. This equation will not hold true. So Maxwell fixed this equation. How he fixed this was by introducing a term he called the displacement current. Okay, so this equation now is modified so as to cancel off the extra terms that you get, because the left hand side when you take the divergence has to cancel. So the right hand side you get a non-zero term for the non-steady current. So to cancel off that term, he introduced another term which is called the displacement current. I'll write it out now. So mu naught J comes from your Maxwell, the Ampere's law, and the term he introduced is epsilon naught dE by the partial derivative of E with respect to t. Okay, so this is actually called the displacement current. Now any book on electrodynamics will give you the derivation for this. It is pretty simple why he introduced this term, but it is enough to know that this is the term he introduced and why he did so. Okay, so to understand what the four Maxwell's equations are. So therefore this final equation now will get modified into this mu naught epsilon naught dE by dt. Okay, so these are your four Maxwell's equations, and in the next lecture we will continue to develop these and understand these. Okay, so and how it applies in our problems.